Hello everyone, we want to continue on doing some more problems for you, sample problems, and in this video I'll try to cover a couple of problems. So the first problem is somebody claims that oxygen gas at minus 113 degrees Celsius and 3000 kilopascal can be treated as an ideal gas with an error of less than 10%. Is this claim valid? So remember that the ideal gas is different from the real gas, and real gases, when you want to consider it to be a real gas, you have to use the z factor, and that basically accounts for the deviation from ideal gas assumption. So what you need to do here is to calculate the z factor and see if your z factor is close to 1. If it's close to 1, then probably the claim is correct, but if it's not close to 1, then the claim is basically not valid. Alright, so let's see how should we do this. This is just a single ideal gas, single component. So you have your oxygen, right, and the temperature is minus 113, so you have to convert it to Kelvin. So this is in Celsius. Plus 273, that makes it Kelvin, so that's 160 Kelvin, and your pressure is equal to 3000 kilopascal, which is equal to 3 megapascal, right? Because that's 1K, and then this is 10 to the 3, 10 to the 6, so that's megapascal, 3 megapascal. Now we need to find the z factor. So for oxygen, you can find the data from the table. You need to find the critical temperature, which is 154.8. I believe table A1 or A2, one of these tables, give you the data on critical temperature and critical pressure. So you need to refer to that table, find this information. And the way we calculated the z factor was first to calculate the radius temperature and pressure. So the radius pressure is your pressure divided by critical pressure. So in this case, your pressure is 3 megapascal and your critical pressure is 5.08. So if you divide these two by each other, you get 0.5905. Critical temperature is T divided by T critical, which is your temperature is 160 Kelvin divided by your critical temperature, which is 154.8. You divide these two by each other, you get 1.033, right? Awesome. Alright, so what you need to do now is, since you have these two data, you have to go to table A15. So I guess you can see it from here. This is actually a chart, so chart figure A15 on your book. So there are two figures here to calculate the z factor, and the top chart is low pressure if your PR is between 0 to 1, which is the case for us in this problem, and this is for 0 to 7, so intermediate pressure ranges. Now it's better to use this one because our PR is between 0 and 1. So in this case, our PR is 0.59, which is very close to 6, and 0.6, and our temperature is 1.033. So you start from the x-axis, 0.6. You go up until you hit the line which represents your the TR equal to in this case 1, right? So you have to go up all the way until you hit the line. You see the TR value is written here, and your TR value in this case is equal to 1, right? So which is this line, TR equal to 1, and it should hit 0.6, so it's somewhere here, 0.79 or something like that, very close to that. So if you use the table and you read this value, then you will have the value of z factor from the table somewhere around 0.79, which has a huge deviation from basically z factor equal to 1, which is the assumption for ideal gas. So therefore what we say is the claim is not valid, because at this condition the z factor is 0.79, therefore the gas is not ideal. Okay. Alright, so that's for this problem, and let's do one more problem, and let me go to the next page. So we have water, and find the following properties using the given information. So we wanted to find, in this case we want to find pressure and X. If we have the information about the temperature, and H is the enthalpy of our water, right? So let's start with part A, since we have the pressure and we want to find the X. Alright, so the information that we have here, we should refer to tables that are related to the water, right? Okay, so part A, temperature is 140 degrees Celsius, right? And the enthalpy is equal to 1800 kilojoule per kilogram. And for this T saturation, if you assume that your water is at 140 degrees Celsius, you can go to the saturated vapor liquid mixtures, which is table A4. Go table A6. Table A5 is the pressure based, table A4 is the temperature based, and if I assume that my temperature in this case right now is 140, which is not, I am still in table A5, sorry, table A4, which is here. Okay, 140 is here, you can see that. You can read all the properties, the enthalpy values, you can read the specific volumes, which in this case doesn't help us, right? The way it helps us is basically to check the enthalpies and look at the values of HF and HG, right? So if we read if you go to 140 and read those two values, I'm gonna write it for you here, based on the table. HF is equal to 589.16, HG is equal to 2733.5, both of them kilojoule per kilogram. And what is our H? Is 1800, right? So which is between HF and HG, saying that our mixture is in two phase, because our H is between HF and HG. So H is less than HG, greater than HF. Therefore we are dealing with a saturated vapor liquid mixture. Now we need to find the quality. Of course, it says it asks us to find the quality and find the pressure. So if we go to 140 again and read the pressure, that's the pressure because that's the saturation pressure, 361.53. So that would be P equal to P saturation, 361.53 kilopascal. And now you can find the quality. So remember the equation for quality, we had multiple equations. You can use the enthalpy as well. So that's H minus HF divided by HG minus HF, right? So our H is 1800, HF is equal to 589.16 divided by 2733.5 minus 589.16, 0.5647. That's the quality, right? And we found the pressure as well, right? Just to remind you, if you have a pressure specific volume or enthalpy or internal energy, and then you have this phase diagram, then whatever is inside is two phase. Let's say this is your pressure, in this case 361, and this is called HF. This is called HG, could be UF, UG, or nu F, nu G as well, right? So since your H is between these two numbers, then you are definitely within the phase envelope and you are in two-phase system. Alright, that's it for part A. Part B. So in part B, we have the information about the temperature and pressure, and we are going to find the enthalpy and phase description, right? So temperature is 80 degrees Celsius, pressure is 500 kilopascal. So what I would suggest you to do in this case when you have temperature and pressure is to go and check what would be, if you assume that your this temperature is the saturation temperature, what should it be its pressure? What should be the pressure in that specific temperature, right? So you go to the water and you go at 80 degrees Celsius, which is the case for our problem, and the pressure, if you are in two-phase, your pressure should be 47.416 kilopascal, right? So I'm gonna write that. If you assume that your temperature is saturation 80 degrees Celsius, then your pressure should be equal to 47.416 kilopascal. And what you need to do is simply to draw the PT diagram in this case. So this is my PT diagram, and it looked like something like this, right? And at 80 degrees Celsius, my pressure is 47, right? Now tell me, at this temperature, what is our pressure? It's 500, right? So your pressure is more than what it should be at the saturation in two-phase. So if you are above this temperature, which is if you're above this pressure, which is the two-phase, then you are in liquid, right? Remember this. So our phase is basically compressed liquid, and this is the phase description, right? Here is liquid, here is the vapor. If our pressure was less than this saturated pressure, then we were in vapor phase, right? Now, if you wanna find the enthalpy, you can estimate the enthalpy of this compressed liquid just by looking the HF in this table. Okay, so HF, because your enthalpy does not change significantly from the bubble point line all the way to the compressed liquid phase, then you can use the same HF as you see here. Okay, so at 80 degrees Celsius, you go to the HF, because we don't have a compressed liquid table for water in this case. We're just gonna use the HF instead, 335.02. Okay, so our H is almost equal to HF, and that is 335.02 kilojoule per kilogram. Again, if you have the pH diagram, two-phase envelope, this is how it changes in the compressed liquid phase. You see, as the pressure changes significantly, your H value does not change really much, right? So that's it, I guess. And that's problem number B. And then in number C, quickly, we need to find the temperature and the phase description for pressure and enthalpy. This one you can try it yourself and see if you can solve it. What you should get for this problem, you need to do interpolation, and it's not more difficult than the previous problem. So try to do this problem and see if you can do this.